Consider this word problem a chin brace, and we're asked to find the value of these two forces. They're identical forces, with the resultant force up the middle here to be equal to 2.25 newtons. Before we start the word problem, let's have a look at our equations. Here they are. And we're going to resolve vectors into their x and y components. It's difficult to work with a vector that is on an angle. It's easier to work with vectors that are completely horizontal or completely vertical. It's easier to add coplanar vectors that are horizontal or vertical than it is to work with something that is on an angle. As a result, we're going to resolve vectors to their x and y components. What you see here, ax, that's the x component called ax, is equal to the magnitude of the vector itself, a. A is the magnitude of the vector. Magnitude of that vector going along there. Cosine theta, and theta is the angle. It doesn't have to be from the x-axis. It could also be from the y-axis. Theta is the angle. And that angle can be either this theta, it can be here, it can be there, okay? Or if we have a vector going this way, it can be here. Any one of these. And this equation, once you understand how it's used, will work for all of these scenarios. First one, it says a cos theta. Now please see my other videos explaining how vectors are resolved into their x and y components. Even though it says a cos theta, a is just simply the magnitude of the vector. I can also write, if this were the vector, has a magnitude of m. And then the x component here could be m cosine theta. Or this magnitude here can be a value of f, in which case, if this has a value of f, and this is theta, then the x component then is f cosine theta. This value f or m or a is just simply the magnitude of the vector itself. Having said all of that, and this is for the y component, let's go back to the word problem. And we're going to solve this by resolving these two vectors into their x and y components. So let's redraw this. Let's see, I'm going to continue here. I'm going to draw an xy plane. Here's the x-axis. And this being the y-axis. I can choose now which way is going to be positive. I'm going to say to the right is positive x and going up will be positive y. So all forces going up will be positive. All forces to my right will be positive. And then again, going downward will be negative forces, and in the negative direction, any forces going that way. Let's look at this one right here. I can rewrite this force here. You can imagine the xy plane. This is the F force going in that direction. So I'm just going to simply redraw it here. And it is an angle of 65 degrees above the x-axis. And I'm going to redraw this one here. It has the same value. F and F means they have the same magnitudes, 100 pounds or 100 newtons, 20 newtons each, whatever the value might be, they're going to be the same. And this one too is at 65 degrees going to the right. When we resolve these two vectors, we're going to get x and y components. This will be the x component of this vector, and here's the x component of that vector, and then there'll be the y components as well. And it will look something like this if I continue on here pictorially. If I want to find the x component, I'm going to draw a vertical line parallel to the y-axis to give me an idea visually what the x component is for that vector. Here it is. And the same thing here. The x component for that vector. And the y components. For this vector, the y component would be here. Again, I ask you to see my other video, which I have posted in resolving vectors. And so this vector here has been resolved into its y component pictorially. And that one. These two vectors now can be added together. And to do that, we place them tip to tail. So I can take one vector, let's take this one, and move it on up. Something like this. Now the total resultant vector, that's all of this, would be the resultant vector, which is right here. The total value of this resultant vector, or the two y components added together, needs to equal, the resultant vector needs to equal 2.25 newtons. As for the x components, this one here being using this terminology with f cosine of 65 and f cosine 65. One is going in the positive direction, the other is going in the negative direction. Therefore, the sum of the forces in the x direction plus this value minus that value is 0. In other words, his head isn't going back and forth. Okay? These two forces cancel out. The only one that we're interested in is the two forces pulling up on his head as a result of these two. So let's move this over here and do it mathematically now. I'm going to split it up. We're going to look at this vector first. So I'm redrawing the xy axis. And I'm going to look at resolving this vector. It has a value of f, and this is what I'm looking for, that value of f, at 65 degrees. And the y component, I don't need the x component. The y component for this vector, for this one, is going to be the magnitude of the vector itself, which is f. In our case, it's f. It could be labeled or a, it could be labeled as m. Regardless, the general equation, as we saw here earlier, is one of these two. Since the angle is here, adjacent to the x-axis, we want the opposite, and that'll be sine. So f sine theta will be the value of this component for this vector, or that force. Doing the same thing now for the other force, right here. And this is the force going to my right. Resolving that one into its y component, which would be this vector, and 65 degrees. The value then of the y component is f sine theta, theta being the 65 degrees. This vector plus this vector added together has to equal 2.25 newtons. We can write that down mathematically. This vector, or the component of the original vector, this magnitude, sine theta plus f, these f's are the same values, so I can just use f and f for this one. F sine theta has to equal, as we said earlier, 2.25 newtons. Putting in the numbers now, because we know what the angle theta is, and we're looking for the value of f. F sine of 65 degrees plus f sine 65 degrees is equal to 2.25 newtons. At this stage of the game, the physics is done. What we need to do now in order to solve the problem is use algebra. So let's go ahead and now just use algebra in order to solve for f, the value of the force. There's a couple of different ways we can solve this, but I'm going to factor out the value of f. And these are two terms. Each of them have the value of f within it, so I'm going to factor the value of f out of each term, and it looks like this, factoring out f from this term and from that term. Sine 65 plus is equal to 2.25 newtons. Now you could go in your calculator and determine what sine of 65 is plus the sine of 65. I'm going to leave it the way it is because that is a number. Looks different, but it's still a number. We want to isolate f. This is just one number, so in order to isolate f, I'm going to divide both sides by this term. And in order to move it to my right-hand side, that would look like this. Isolating f, dividing both sides by sine of 65 plus sine of 65 is equal to 2.25 newtons divided by this term. I'm going to leave it in brackets to show that that is actually just one number. And to show that, let's carry on. 2.25 divided by, putting this in the calculator, adding them up, the number is 1.812615574. Taking 2.25 divided by this value will give us the value of f, which we are seeking. So force F is equal to 1.24130159. Once you do the sine of 65 degrees, any degree, it becomes a dimensionless number, so there's no dimension behind it, no units. The only units left over then is the newton, and this will have the final value of a newton. And all forces have a value of a newton. Last thing we need to do is reduce this to proper significant figures. Where do we find that? Well, we go back to the original word problem. And the measurements that were made, again, I have a video regarding significant figures and measurements. 3 significant figures for the angle, and 3 significant figures for the final force, the resultant force. So therefore, our final answer can't be any greater than 3 significant figures. So we're going to go to 3. Force then is approximately equal to 1.24 newtons. All forces have a direction. Remember, this is a vector after all forces have a direction. So we need to give this a direction. That force is pulling in that direction. This force is pulling in that direction at 65 degrees. A simple way to do that, because we already have a sketch, I just simply write 1.24 newtons in the directions shown. Effectively, this is the solution. Well, let's take this a step further. What is a newton? I'm going to apply 1.24 newtons to this individual. Yeah, I don't know. What's a newton? I work in pounds. I understand pounds. I don't understand newtons. So let's do this one more step and go to pounds. Give you a better idea of what this question is actually asking. So look at it this way. What's happening here, even though it isn't completely shown, there's a couple of things have been removed, so I'm going to add them. This is a rope, and it's wrapped around a pulley. And the rope goes around the pulley, and it's hanging down. And there is a weight down here. And that weight has a value of 1.24 newtons. We just calculated. And the same thing is happening to the other side. There's a rope. It's being wrapped around the pulley. As the rope wraps around the pulley, it's going to hang down at the other side. And here also is another weight. Same value, 1.24 newtons. Yeah, and weight is a force. These two together will give a resultant force on his head upwards of 2.25 newtons, which we calculated. Again, 1.24 newtons, what is that? let's change this to pounds. That's something that we understand. From our conversions, here's our conversion table. Using forces, we can see that 1 Newton has equivalency of 0.2248 pounds. I'm going to use that one. 1 Newton is equal to 0.2248 pounds. Doing a conversion now, changing this value of Newton into pounds. 1.24 newtons, and I made a video regarding conversions. Multiplied by, I'm going to place newtons on the bottom, pounds on the top. It's 1 Newton and 0.2248. Then the Newton and the Newton cancel out. This becomes 0.27875, and the only unit left over is the pound. Rounding this, approximately 0.279 pounds, just over a quarter of a pound. But this is the same as saying the weight being pushed down here is in imperial terms 0.279 pounds. Now we have an idea of 1.24 newtons is just about a quarter of a pound, little over. 0.225 pounds is a quarter, so it's over a quarter of a pound. And the same thing on the other side. In imperial terms, put two weights on either side of just over a quarter of a pound would give us a resultant force upward, which we calculated of 2.25 newtons. And what is 2.25 newtons in pounds? We'll simply go ahead and do the conversion here. And we can read the newtons on the bottom, pounds on the top. And follow the units, and the numbers go for the ride. So it's 1 Newton, 0.2248. Doing this multiplication, the answer is 0.505 pounds. It's actually a 0.505 pound force. But that's another story, which is a whole video all unto itself. So we're putting upward force of 0.5, just a little over half a pound, by adding these two weights in this configuration. The actual force being applied to the head upward is just over half a pound. Sideways, well, the two x components, they canceled out, so there is no forces in this x direction. The sum of the forces in the x direction is 0. They both cancel out. So the only force being applied to the head right now is the upward force, the resultant force of 2.25 newtons. And in pounds, looking at it this way, if we were to take this, just to show you that, does this make sense? Let's take these two forces, and instead of placing them on an angle, we're going to bring them in and put them directly on the head. Directly here, pulling straight up. So I'm going to redraw this, and I'm going to take that quarter of a pound, or 279 pounds, and put it straight on the head, pushing upwards. If I were to redraw this, here's the gentleman's head. He has his neck. Okay. And I'm going to place the whole weight completely upward, and the rope is going to come around the pulley. Pulley doesn't really change anything other than the direction. And I put that 0.279 pounds coming down here. So that full pound, 279, is now being applied to the head upward. And I do it again for the other side. And there's a pulley, and it comes down, so I have that weight here. So both weights are pulling down. All of the weights now is being applied to the head directly upwards. We're not doing it at an angle anymore. It's going straight up. Therefore, the total force in this configuration being applied to the head upward is a summation of both of these two. That 279 is transferred to the rope itself right here, 0.2794. So add these two together. And the resultant force upwards in this configuration is equal to 0.279 plus 0.79, and that's equal to 0.558 pounds. And that makes sense. If I were to apply the total weight, both of these total weights, to the head upward, the total force upward comes to 0.558 pounds. As we do it towards on an angle, however, more of it and more of that force is being put on it horizontally and less is being put on it vertically. As a result, the vertical component drops down, as you can see. No final answer. The force that needs to be applied to this head here in this configuration is equal to approximately 1.24 newtons, because we are going to stay in metric. You can, if you wish, change over to imperial, as I have done, in order to get a better understanding of the problem.